Greetings, ladies and gentlemen, boys and girls. Today we're going to talk about linear programming, which is a type of mathematics in the branch of operations research. Operations research. And what's I think is interesting about this is that this is, first of all, this is likely the most current mathematics that I myself know. And this was developed back in the 1940s by the British. 1940s, I wouldn't necessarily commit to which year that was. But, and it gets its name operations research. It's actually literally talking about military operations. Now, this was a problem that, well, first of all, here's my problem is I got to draw an airplane. So here's an airplane. This is the problem that the British had, right? So they had their kind of like bombing planes that they'd send out, right? And they'd go in and like bomb Germany or whatever, and they'd drop their bombs. Right? Here's a bomb. Bomb. Right? And they would send in their planes, and they'd kind of, here's like a top view. So they'd have, these are planes, by the way. And they'd send in their planes, right? And they'd send in one wave of planes. And they'd go in and then like they'd see their city targets and they'd be like, aha, there's the city, let's bomb it. There's, you know, all sorts of different stuff. And they'd send in their first wave of planes, and their first wave of planes would do pretty good. They go right, and they'd bomb the city or whatever. But then they were realizing that their second wave of planes, right, because they kind of sent them in stages, their second wave of planes, if they sent them in too early, there was still too much like smoke and debris in the air that the second wave of planes couldn't hit their targets. Like they couldn't visually get a confirmation, right? Because they didn't have like, you know, GPS stuff and targeting and all things like that. Or I imagine they didn't even have, you know, night vision capabilities or stuff like that, or ways of heat vision to see through the smoke. I imagine they were limited to those capacities. I think it was literally like I see the building down there, I'm going to release the bomb now so it, you know, by the time it's over that building, it will be on the ground, right? Stuff like that. So they were trying to figure out what do we do regarding, right, this distance, right? And the other problem was if they had the distance too far apart, well, then what happened was that the German dudes, they would be getting on like their little anti-air machine guns, and like there'd be the little dude up here and he'd go, ah, and then they'd be like on their little turret thing and go, right? Because they, after the first wave came through, they're like, sound the alarms, and like all sorts of alarms would go off, and then these guys would all be ready. Let's see, let me actually give them like a classic, awesome little spike hat, which I was always wondering. Actually, I don't know if they had those spiked hats back in World War II. Maybe it was just World War I. But what's the purpose of the spike on their hats? Like, do they actually like charge dudes like a rhinoceros? Like, is that part of like blitzkrieg tactics? I don't know. That'd be pretty cool if that's what the intent was for. I don't know. I would just like, I'd be scared of a dude with spikes on his hats. I mean, I guess the Vikings had horns, right? Maybe they didn't literally use those either. But anyways, but the problem was if this distance became too great, then these guys are on their anti-air guns, their AA guns, and then like they're losing most of these planes and pilots because the Germans were prepared. So they were like, all right, we've got to figure out what is the optimal solution for this. And not only was that something that they optimized, they also figured out what was the optimal pattern, right? What was the arrangement of their planes that would be the optimal solution. And that was one thing that had spurred on the need for this new branch of mathematics. Operations research is an optimization technique that is non-calculus based. All right, and what's cool is you can actually optimize hundreds of variables simultaneously. All right, other similar situations that they had that they ended up using operations research to help win the war was, right, so they had like ocean naval combat, right? And there would be like boats, and some of these boats would just be like little supply boats and stuff, right? And they tried to figure out, is it better to send, all right, lots of little supply boats going out, right, kind of all spaced apart throughout the ocean, and sure, some of those boats will get found by the enemy and blown apart, or is it better to have like one big fleet of boats where like you've got like all of your awesome like defensive ships and everything like that. And you've got all of your boats together, which increases the chance of them being found. But if they're found, because there's so many of them, they'll have a better chance of defending themselves, right? So what was the risk reward there? Is it better to have them scattered in small pods all throughout the ocean, kind of running their supply lines so that, it's less likely they'll be spotted? Or is it better to be able to defend them better? And when they ran the math on that, they actually found it was better to have huge convoys of boats, huge fleets, armadas maybe, if you will. And even though it pretty much guaranteed the likelihood of them being spotted, it minimized the losses of their ships. Other things that they'd considered was, all right, so here's your Mr. Soldier that you're sending into war, right? And you're sending him in, and he's got his gun, right? And he's like, all right, so I've got my gun, my awesome rifle. And you've got to figure out, okay, how many bullets do we give this guy, right? Like, so he's got his little clip, right? There's his little clip, pa-ching, and then he like loads it in there, right? So how many bullets do you give your soldiers, right? At what point are you having them carry too much weight that they can't efficiently run from like cover to cover, right? To like hiding behind like a barn or something, I don't know. Right? Because you want them to hide from cover to cover. Is it going to slow them down at some point where, they're carrying too much gear, they're getting fatigued, and now they can't efficiently move about? Versus, are you giving them too few bullets that they just get like one bullet? And it's like, well, I hope you enjoy that one bullet. Use it wisely, right? Where, sure, you can move around really fast, right? But then, like, when you get there, like, you're like, I don't know if I want to shoot. Like, I got one bullet, right? So there's all sorts of different situations like this that needed to be found out, right? Because, I mean, when it came down to this wasn't just about, maximizing profit for your company. This was about, possibly defending your nation, determining who's going to be in charge of you, right, in the next decade, and also like determining whether your guys are coming home, right? Like, are they going to be killed? Like, what's going to happen to them? So this was like a real serious problem, and it was these British mathematicians who ended up finding and discovering this whole branch of mathematics that allowed them to optimize all of these problems and figure out exactly what the best solution was. And it turned out that the more details and the more data they had on it, the better their solutions were able to become. All right, so this is the idea of operations research, right? You can tell I'm excited about this stuff. I love this stuff. So we are going to take a look at, let's see if I can get a non-blurry version of this problem. Got the blurries here. So we're going to look at this primarily from a business perspective, I guess, is most of the problems we'll be doing. Let's see. There. And it turns out all of the Fortune 500 companies use these techniques. We're going to specifically be dealing with two-dimensional operations research problems where we just have kind of two variables and we'll be able to graph our solutions. It turns out the multivariable ones are solved using a type of matrices, I guess, and can be solved on computers and stuff. And they're used for all sorts of different things, like figuring out how to maximize profit, or have the most efficient delivery route if you're UPS, or how to coordinate all of the airplanes in the air and their landing and their schedules and everything like that. So it's used for all sorts of different things, and I find it to be a pretty interesting field of mathematics. So here we go. This is, by the way, example 1 on page 112 of our text. It says, you don't have to write it down. You could just write example 1, page 112. Suppose a lumber mill can turn out 600 units of product each week. To meet the needs of its regular customers, the mill must produce 150 units of lumber and 225 units of plywood. All right? If the profit of each unit of lumber is $30 and the profit of each unit of plywood is $45, here's the question: how many units of each type of wood product should the mills produce to maximize profit? So we're going to use our typical word problem solving format, VESA, VESA, I don't know. which it stands for variable, equation, solve, and answer. So for our variables, typically the variables of our problem are found within the question, right? It says how many units of each type of wood product should the mill produce? So I'm going to have, there were what, 2 types, right? So I'm going to call these X and Y. But if you wanted to call it L and P for lumber and plywood, it doesn't matter to me. So let's define these. What are X and Y? What should X be? Lumber. What about lumber? Is it the cost of the lumber, the length of the lumber? Yeah, so it's the number or unit, number of lumber produced, right? And we want to be specific with our labels so that way we can better answer the questions later. And let's see, and then Y is going to be the number of, or units of plywood produced, right? And now that I have my variables defined, I'm better able to interpret my limitations, right? Because I've got a lot of little facts floating around. So here's my E in VISA for equation. Technically, most of these are going to be I's, inequalities, but whatever, we'll still call it E. So let's see. What do I know about X and Y? It says, suppose a lumber mill can turn out 600 units of product each week. So what is a relationship between X, Y, and 600 we could make? 600X?
Would be like 150Y plus 225X.
No. Well, let's see. I know that this is X is the number of plywood or lumber I can produce. Y is the number of plywood. At most, I can produce 600. So I'm going to say that the number of lumber plus the number of plywood relates to 600. Now it's at most 600. So what inequality, what relationship could I use here? Less than or equal to, right? So there's my first fact. Then it says to meet the needs of its regular customers. So here's, right, they must have gathered this data. They must have figured out, oh, this is what the regular demand is. And the more data a business can gather, the better you can find the most optimal solution. So it says to meet the needs of its regular customers, the mill must produce 150 units of lumber. So X relates to 150. How? It's got to be at least that much, right? To meet the needs of our customers. And then there must be 225 units of plywood. So Y has to be greater than or equal to 225. All right? So those end up being my inequalities. Now, normally in real-world problems, a lot of times you'll have to also say something like, also you have to have X greater than or equal to 0 and Y greater than or equal to 0 because you can't make like antimatter plywood. Although that would be pretty cool to have a house made out of antimatter, it doesn't fit the constraints of this real-world problem. However, I don't need to say X is greater than or equal to 0, and why is that? Why don't I have to specify X being greater than or equal to 0 for this particular problem? Well, I can't have negative number of plywood, but, well, I've already got a constraint. Saying X is greater than or equal to 0 and X is greater than or equal to 150 would be redundant. It wouldn't be necessary for me to specify that constraint since I've already got this one, which is more restrictive. And the same thing for Y. I don't have to say that Y is greater than or equal to 0 because I have this more restrictive constraint already at play. And then I've got an equation related to the profit, right? So I've got a P of X comma Y equation. This is an equal one, not an inequality. Where how much money do I make per unit of lumber?
30.
So 30 times what? 30X would be the amount of money that I profit from selling all of my lumber. And plus what? 45Y is going to be my total profit. All right, so here's my setup. Now let's see if we can figure out the solution. So to solve this, the S in VESA, it looks like I could take this x plus y is less than or equal to 600. It looks like I could put that in slope-intercept form, subtracting x from both sides. That could be helpful. Y is less than or equal to negative x plus 600. Right? And now I'm just going to have to go through and graph these. So I've got, what, 3 inequalities that I've got to graph. And I got to figure out their common shaded region. I have to find the vertices and then figure out which of those vertices will maximize our profit. So let's see. I might, you know what, I'm going to check. Oh, what did I just hit? Yikes, it's going to yell at me. There we go. Aha. I'm going to actually make a new little graph here, just for the sake of ease. Actually, you know what? I don't think it lets me make one at x greater than or equal to 150. That's fine. So I'll have one being at 225. I'll have one being at negative x plus 600. And the other one, I'm going to have to actually, let's see. 100, 150. Let's see. I should be able to. There's one. It's not graphing it very well for me, is it? All right, there they are. They're hiding there. You're just not showing them very well. What did you do? Computer. Let's see, it's not showing the whole line. Why? Let's see. Well, I can regraph those. 225. Now it's showing the whole thing now that I'm zoomed out far enough. And negative x plus 600. There we go. And then let's see. I've got a trick I can do. I think I can plot a point. Let's see, what was the x equals 150? So I'm going to plot the point 0, 150. Nope, 150, 0. So there's that point. And because x equals 150 is not a function, I don't think I have a good way of graphing that. But I can construct a perpendicular line through that point. So that's good enough. Here we go. Line style, medium. There we go. All right. So let's see. For my x1, it's greater than or equal to. So that's shaded to the right. For my y horizontal, it's greater than or equal to. So it's above. And for my diagonal, it's less than or equal to. So it is in fact under that. So it appears as though this would be my graph. Here we are. So you would have graphed this somehow by hand. It's fine. It'll work out. Let's see. And now we've got to figure out what are our intersections. Well, let's see. Actually, our shaded region ended up being the interior of this triangle. But once again, I want to emphasize that's not necessarily always going to be, it's not the inside always of your polygon. Okay? And I want to figure out, okay, so I've got point A, I've got point B, I've got point C. What does the x-axis represent? What did x represent? Well, what does these x values represent is what I'm asking. Right, units of lumber, right? I just want to make sure we reconnect what those are. And what did the y-axis represent? Right, units of plywood. So number of plywood there, right? So so that's what those were. Let's see, what are the coordinates of point A in this case? (150, 225). I believe that makes sense. 150, comma 225. What are the coordinates of point B here? It's 150 for the x again. It might, maybe it's around 450, but let's actually find out for sure. What I could do is plug this x into this equation for x and find the exact y value. So negative 150 plus 600 does happen to equal 450. right? So that's not that bad. And then let's see, point C. Well, I know that the y value is 225 because it's on that horizontal line. And the x value, a little tricky. Well, I could plug 225 in for y and solve for x. So subtract 225 from both sides. What's that going to be? 375 for the x value? And that looks like it's graphically about right. But if you were graphing this by hand, I imagine it would actually have been more difficult to, have your graph be super accurate and consistent tick marks that you would have been able to read that, right? So those are my points, but now let's plug them into 30x plus 45y. So let's figure out our profit for each. So 30 times 150 plus 45 times 225. So let's see, so that's 450 plus 225 times 45. Nope, that's not what I plugged in. 225 times 45 plus 30 times 150. Sorry, did I say 30 times 150 was going to... What did I say earlier? I said something. It's going to be 1,000. I think I said 100 a moment ago. But the total here is 14625, so $14,000, 625. Let's plug in point B, so 30 times 150 plus 45 times 450. This one's going to be a pretty penny, if I'm not mistaken. So 45 times 450 plus 30 times 150. Is 24,750. And then we'll plug in the last one, 30 times 375 plus 45 times 225. And calculating these. Here we are, and I get 21,375. So now interpret this for this business owner. Let's put this into an answer form. A maximum profit of what? Looks like 24,750 is earned by producing what? 150 lumber and 450 plywood. Right? So, and sometimes when you find the answer, you might realize, oh, we could actually really increase, like if you could increase your productivity from 600 to this, then, maybe it makes sense to kind of move one of these constraints, right? The business owner might have some control over some of these constraints. Or if he knows his, brother down the street is also running a factory that's making lumber, maybe he could just be like, hey, let's just forget about the whole lumber market and let's just focus on making 600 things of plywood, and I'm going to just be a plywood factory, right? And you could kind of weigh out these different options and figure out what would make the best sense in order to optimize this situation. Let's see. Now, there are sometimes possibilities where an optimal solution can't be found. Like, for instance, what if our shaded region was this up here? Maybe there's an infinite amount of profit that could be earned. But in those cases, sometimes what you need to do is figure out maybe there's some other constraints that we're not considering. Maybe it is physically impossible to make infinite lumber and plywood. And that's probably where they found out this constraint, that they could only produce a maximum of 600 a day. And that's where that diagonal line came from. Right? So sometimes for an unbounded answer, you end up realizing maybe there's some limits that you haven't yet measured, right? It's also sometimes possible to have an infeasible solution where maybe like my shaded region just never overlapped, right? What if I at most could only produce like 300 a day, And then by doing so, I'm not even meeting those customer demands. Like my shaded region would have wanted to be this way, and this way, and I wouldn't have had a solution at all, right? So sometimes that can occur as well, and then, you know, for the business owner or whatever you're considering, you'd have to try to figure out what sorts of situations can you change around. Let's see, I think for sake of time, I'm going to cut this video short. I might end up recording at another point another example of this concept, but this is the general idea. Interpret your variables, define them, write your constraints, graph them, find the shaded region, find the vertices of that shaded region, plug them into your either profit equation that you're maximizing or your cost equation that you're minimizing or whatever it might be, and then be able to answer the question. So the general outline is the same, but we're going to take a break now. So thank you, Internet friends. Bye-bye.